हेलो फ्रेंड्स, कैसे हैं आप? बच्चों, बड़ा ही प्यारा टॉपिक रहता है 10th क्लास के बेस पे। सीबीएसई बोर्ड में 101% तो नहीं, लेकिन 90% और 80% अगर देखा जाए तो कहीं ना कहीं सेक्शन बी और सेक्शन डी और सी में पूछा जाता है। टॉपिक का नाम है थेल्स ने दिया है, बीपीडी बोला है उसको, बेसिक प्रोपोर्शनलिटी थ्योरम। और 101% आने के चांसेस इस साल होने चाहिए मेरे हिसाब से, है ना? होने चाहिए। बड़ा प्यारा है। कह रहे थे एक अगर ट्रायंगल बनाया जाए और उस पे कोई दो साइड पे एक पैरेलल लाइन, थर्ड के रेस्पेक्ट में कोई पैरेलल लाइन अगर ड्रॉ की जाए, तो जो इंटरसेक्ट करती है पैरेलल लाइन, उन दो जो साइड है जहाँ इंटरसेक्ट किया, जिन दो साइड को इंटरसेक्ट किया, उनका रेशियो जो रहता है वो सेम रहता है। ये बात कही है। इंग्लिश में बोला जाए तो बड़ा प्यारा है। इफ अ लाइन ड्रॉ पैरेलल टू वन साइड ऑफ अ ट्रायंगल टू इंटरसेक्ट अदर टू साइड्स इन डिस्टिंक्ट पॉइंट, द अदर टू साइड आर डिवाइडेड इन टू इन सेम रेशियो। मज़ेदार है, इसको थोड़ा पढ़िएगा, आता ज़रूर है। और चैनल को सब्सक्राइब, लाइक और कमेंट भी करिएगा। नाइस।
All right, let's jump right into a really cool concept in geometry, the basic proportionality theorem. You might also hear it called Thales' theorem. Now, this isn't just some random rule from a textbook. It's a truly beautiful piece of logic that shows us the hidden order inside simple shapes.
So here's the deal, and it's almost like a magic trick. You take any triangle you want, and you draw a line that's parallel to one of its sides. When you do that, something amazing happens. That new line divides the other two sides into perfectly proportional pieces, every single time. It's like a secret rule of harmony created by just one little parallel line.
Okay, but how can we be so sure? How do we know this isn't just a coincidence? We need proof. So let's treat this like a detective story. The theorem is our mystery, and we're going to follow the clues step by step to crack this case wide open. Now, every good detective needs a secret weapon, and ours is going to surprise you. We're not going to solve this with a bunch of complicated angles or side length calculations. Nope. Our key is something much more basic, the simple formula for the area of a triangle. That's right, area is going to unlock this entire mystery for us.
But before we can start collecting evidence, we need to set the scene. Here's our construction plan. First up, we're going to connect points B to E and C to D. Next, we need to find the heights of our triangles, so we'll draw some altitudes. Those are just lines perpendicular to the base. We'll draw one called EN, perpendicular to the side AB, and another one, DM, perpendicular to AC.
And voila! Here is our completed diagram. Now, I know, it suddenly looks a lot more complicated, right? All these new lines crisscrossing everywhere. But don't worry, trust me, we're just going to break this down piece by piece. All right, let the investigation begin. Our first piece of evidence, we're going to find it over on the left side of the triangle. Our mission is to figure out the ratio between that little segment AD and the segment DB right below it. To do this, we only need to look at two triangles for now. See that green one up top? That's triangle ADE. And see the light blue one on the bottom left? That's triangle BDE. Let's just focus on those two and see what they tell us.
And remember our secret weapon? The area formula. Just a quick refresher, the area of any triangle is just 1/2 times its base times its height. This simple little formula is about to do all the heavy lifting for us.
Okay, let's put it to work. For our green triangle, AD, the area is 1/2 times its base, AD, times its height, EN. Now for the blue triangle, BDE, the area is 1/2 times its base, DB, times, hey, wait a minute. It's that same height, EN. They actually share a common height. That's a huge clue.
So, what do you think happens if we divide the area of that first triangle by the area of the second one? Well, the 1/2 on the top and bottom? Gone. They cancel out. And because they share that height EN, that cancels out too. And just like that, all that mass just melts away. The ratio of the areas of these two triangles is exactly the same as the ratio of their bases, AD divided by DB. This is our first major piece of evidence. Let's file that away. We've cracked the left side. So, what's next? You guessed it. We're going to run the exact same play, but this time on the right side of our diagram. We need to find the ratio of segment AE to segment EC. So our focus shifts. We're still using that top green triangle, ADE, but this time we're pairing it with the purple triangle on the bottom right. That's DEC. Same strategy, different players. And just like we did before, let's look at their areas. For triangle ADE, its area can also be seen as half of base AE times the height DM. And for our purple triangle, DEC, its area is half of base EC times, yep, that same height, DM. Once again, a shared common height.
So we divide the areas, and poof, the 1/2s cancel, the common height DM cancels, and we're left with our second key piece of evidence. The ratio of the areas is just AE divided by EC. Our investigation is making some serious headway.
Okay, let's pause and look at our clues. We have one ratio for the left side and a totally separate ratio for the right. But how do we connect them? How do we prove they're equal? This is the point in the mystery where we need that final critical breakthrough. And the critical link, the one thing that's going to solve this whole case, is hidden in those two triangles at the bottom, the blue BDE and the purple DEC. Think about it. Look at our two ratios. The numerators, the top parts, are already the same. They're both the area of triangle ADE. So if we can just prove the denominators, the bottom parts are equal, the case is solved. And this is where a fundamental rule of geometry comes to the rescue. Let's read this clue carefully. Triangles on the same base DE and between the same parallel lines BC and DE are equal in area. That's it. That's the breakthrough, because both of our triangles, BDE and DEC, are standing on the exact same base, DE, and they are literally sandwiched between the same two parallel lines. Their areas have to be identical. And that means the denominators of our two area ratios are equal. The area of the blue triangle is exactly the same as the area of the purple triangle. We found it! We found the missing link that connects the left side of our triangle to the right. We have all the pieces. The evidence has been collected, the critical link has been found, and this puzzle is ready to be solved. Let's put it all together. So, on the left, we have our first ratio of areas. On the right, our second. We already know the numerators, area of ADE, are the same. And we just proved that the denominators, the area of BDE and the area of DEC, are also the same. Well, if the tops are equal and the bottoms are equal, then the entire fractions have to be equal to each other.
And if the ratios of the areas are equal, then the expressions they represent, the side ratios, must also be equal, which means that AD divided by DB is absolutely equal to AE divided by EC. The puzzle is solved. The case is officially closed.
It's a really elegant proof, isn't it? And it makes you wonder if one simple parallel line can create such a perfect hidden relationship inside a triangle, what other amazing patterns and secrets are just waiting to be discovered in the simple shapes all around you?